All right, section 2.1 is titled The Derivative and the Tangent Line Problem. We've talked about this briefly or generally already. So the first part here, you might look at it and say, well, didn't we already talk about that? And the answer is actually yes. But just to remind you what we're talking about when we talk about this secant tangent line problem, secant lines are lines that cut through two specifically different points when you first learn about them on a circle. That's where you first see them when you're in high school, is in a circle form. But it's also true for any general curve. So if we have a general curve here, I'm going to draw it twice so that you can see the difference between the two pictures. So on the first one, if I were to take 2 points on my curve and I were to connect them with a line between them, that'd be a secant line, okay? And I realize it may hit other points too. It happens to the one I've drawn. That's irrelevant to the issue. But I connected 2 points on my curve with a line, and that's called a secant line. So a couple of things just identifiable here is if we let this point right here be C, then this other point over here, the x value for it, we can call C plus h. So we're saying that the distance between these is h. They're h apart. And then in terms of their output values or their y values, this point would be f of c, and this y value's output would be f of c plus h. So over on my other curve, again, if I have that same point C, the idea is to take the point that's h away, like I did before, and to have that point, in fact, I think I'll use a different color for it, get closer to my blue point. So to let the distance between them become almost zero or approach zero. So this red dot, where we would have connected the line looking something like that, is getting closer and closer to the blue dot. So the line that connects them continues to change. Sorry, this is what happens when you're trying to draw it. That's pretty good. So the line that you're moving closer towards, the point that you're moving closer towards alters the line as you're moving. And eventually the point gets so very close that we say that we have approximated the tangent line. So we are letting these distances get really, really close together, holding one of them fixed, my point C, and the other point is moving toward the point that we are caring about. And when we do that, we can talk about the slope of the secant lines and how they're changing. So the slope of the secant line through the points C, f of c, and c plus h, f of c plus h, is given by this equation. So slope is y values divided by x values. I mean, that's what slope is, the change in y over the change in x. So these are the change in two different y values. Okay? And I can't simplify it. There's no, these parentheses don't mean, multiplication, right? They're the function value, the y value at this particular x value. So you see the entire numerator stays the same here, yeah? Once I've written it once, it doesn't change. However, in the denominator, I have two x values that are just identified individually, and if I subtract and simplify them, they do in fact become simply h. So again, what we want is we want that h value to become practically zero. And we've seen this happen on some of the limits that we have done in the earlier chapter that we just completed. When this becomes zero in the denominator, we have to do some kind of algebra manipulation so that it goes away. I don't want 0 in the denominator. That is something I can't actually find a specific numerical value for directly. I've got to do some algebra to simplify. And so what happens is that as we take this limit right here, as h approaches 0, there often is some very nice algebra, and we've seen sort of the beginnings of it back in the last chapter. So if f is defined on an open interval containing c, and if the limit as h approaches 0 of f of c plus h minus f of c over h exists, okay, so we can't have some of these things where they didn't exist. There's no jumps in the things. We can have holes, that's okay. No jumps. No asymptotes. That's not appropriate for this definition. The limit has to exist for this to work. Then the line passing through c, f of c with slope m is the tangent line to the graph. The slope of the tangent line is also called the slope of the graph. So when we talk about the slope of the graph at that particular point, we're talking about the slope of the tangent line to that graph. Just kind of a shorthand notation.
So will this be on the next test?
Yes, it will. And you will find one in its long term. Yeah, so how many of you have had a calculus course before? Can you just show your hands? Okay, so about a third of you. So you will have to do this one time for me on the test, and others of you are going like, what's she talking about? Well, we're about to get into, in section 2.2, some really nice shortcuts to not have to do this every time, and you're all going, yay, those of you know what I'm talking about, but you're going to have to do this at least once on the test, okay? So let me show you what this looks like from an algebraic standpoint, and there's a couple of ways to do it. I'm going to show you both of them. So the directions here say to find the slope of the tangent line to the graph at the given point. And right over here, the definition told us how we're going to do that. We're going to take the limit as h approaches 0 of f of c plus h minus f of c over h, and the c value is the x value I'm trying to find my limit at, so in this case it is 1. Okay, so this is what the definition said I'm going to do. I'm going to take the limit as h approaches 0 of f of the c value, which is 1, plus h minus f of 1 over h. That's what the definition actually said. So we're going to give this a try. Now, it's actually kind of friendly in the sense that we already know what f of 1 is. What is f of 1? It's 5, right? So the input 1 means that's the x value. What is the y value when x is equal to 1? It's 5. They happen to give it to you in the problem. If they didn't tell you it was 5, what would you actually have to do? You just plug the number 1 into the function and it would become 5. I mean, that's what would happen. But this one's nice because they actually already gave that to you. So we have that piece already. H is the item that we're trying to somehow eliminate from the denominator. That is our goal here. Our goal is to get that H to go away somehow, okay? Now this piece that's left in the numerator is the piece that requires work. It says to take the function, and I'm kind of being sloppy here because our function's name is g, so I suppose we should probably call this g in these cases. I'm not going to be too worried about it if you don't, but our function is g. So it's to take this g of x function here, and where x is located, I'm going to replace it with 1 plus h, okay? That's a college algebra concept. I hope that you're comfortable enough with that to see that part of it. So this should say 6 minus, and then the x is going to be replaced by 1 plus h, and it is squared. And then I have minus 5 at the end. There's a lot of algebra there. If it's been a little while since you've done the algebra component of that and you want to come talk a little more about that with me, I'm totally great with that. Just come hang out with me and we'll chat. Please remember that there is not a distribution property of squares, right? This squared here does not become 1 squared plus h squared. That's not true at all right? You have to multiply it by itself. So this actually means I have 6 minus 1 plus h times 1 plus h. And if you wish, you can actually simplify the 6 and the 5 here. We could do that real quick. That's going to be a 1, right? Sorry. Let's do that. So the 6 at the beginning, the 5 minus 5 at the end is a 1. Or you can wait till the end to do it too, it's fine. Okay, cool. So we're going to distribute out the 1 plus h times 1 plus h, and then it will have a negative on it when I'm done. So 1 times 1 is 1. The inside and the outside terms are both h, so that's 2h. And then the last term, h times h, would be h squared over h. Please notice, every single time I rewrite limit h approaches 0. Okay, you guys did awesome on that on your test. I was super, super impressed with how well you guys did with remembering to write limit every time. That was something that was certainly a highlight of your abilities on the test. It was great. So remember that here as well. The limit will still be there until we allow h to actually be plugged in as 0. Okay? So we need to distribute that negative. So we have limit h approaches 0. Still have the 1 at the beginning, and then I have minus 1, minus 2h, and minus h squared. So yeah, look at those 1s. They add to 0, right? They do. And the cool thing that happens, and it will always happen when you're working on these, is that you have eliminated everything from the numerator that did not have an h in it. Right? Look, everything, numerator and denominator now have a component of h. And you're able to reduce. You can think about it in one of two ways. As long as you're careful, you can think about reducing one of the h's like this, because it's in all of the terms. That's okay. Or, if you're concerned that you might lose something along the way, which can happen, instead you could factor an h out of the numerator, like this, and then cancel the h's here. Either way, you're good to go. It doesn't matter to me as long as you're careful doing so. So the limit is h approaches 0 of negative 2 minus h. And the goal, which really was get the h out of the denominator, has now been achieved, because now that there's not an h in the denominator, it's okay to let h be 0, right? And if h is equal to 0 here, then my answer is simply negative 2. Now, I showed every tiny, well, almost every tiny little step of algebra along the way. If you shortcut some of those steps, that's okay. I know for some of you, you're like, why did she take 3 steps to do that? I would have all done it at 1 step. That's all right. You can do that. Just be careful and make sure you don't lose any signs along the way or something like that. Okay, to shortcut a little bit of the algebra, but this is what you would end up with. Okay, now this was very specific. They told you the specific x value or c value that we were looking for, right? They told you it was happening at x equals, what was it, 1, at x equal 1. What happens if they don't tell you that x is equal to 1? Well, that's actually what happens in general. So the definition of the derivative of a function, the word derivative really means slope of the curve, slope of the tangent line. They're all the same thing. The notation for it is a prime, f prime of x. And you'll notice this looks suspiciously like the formula we wrote down on the other page. Very similar. The only difference is that there's an x in there instead of a c in there, right? And the reason is because when they put the c in there, you had a specific value you were doing it at. Our problem was at the value 1. But the reality is that all of the algebra we did and we plugged in the number 1 for, we could have done it in general with x just sort of in there as a placeholder and plugged in 1 at the end as well. So that's what we're going to do on the next problem. We're going to find the derivative using that process where we are not given a value for x. And the formula that we're going to use is a rational function now instead of a polynomial. So this is f of x equals 1 over x squared. So notation, super important. Start with f prime of x, and it equals, and I'm just going to write down the definition from the previous page just so that everybody can see it on there and it didn't change. So that's what the definition said. The two pieces in the numerator we need to change into what they really are based on the function that we're given, and that will change every time. Right? Your function's different every time you're working with it. So the function itself, though, will always go in the second location. So there's no algebra simplification. You're just taking it and you're stuffing it in there. So as I'm working on this, that's the easy part. That's the part you get sort of for free. We get minus 1 over x squared here because that's what f of x is. It's 1 over x squared. The first part is not f of x. It's f of x plus h. Only difference means take my function, and where I have an x, I need an x plus h. So that it looks like that. All hinged upon whatever function I'm given. Okay, so any questions about the setup? Because if you can't get it set up, you're not going to be able to keep going. Where any pieces came from or clarifications. Okay. So the majority of the rest of this problem is algebra. I mean, it's high-level algebra because I've got a lot going on in this problem, way more than the last problem because there's a rational function actually. But it is just algebra, all right? So this is not calculus on this part of the problem. So let's take a look at how the algebra would work out. Again, limit h approaches 0 all the way along until we plug it in. So right now, in that denominator, if I multiply x plus h times x plus h, I would have x squared plus 2xh plus h squared. Minus 1 over x squared over h. Okay, everybody good so far? Kind of messy, and super unfortunate that we're dealing with denominators because the only way we can add fractions together is if the denominators are what? The same. It's just reality, right? Denominators have to be the same. I can't add 1/3 and 1/4 and get 1/7 or 2/7. Doesn't work like that. Got to have the same denominator for us to be able to add fractions. So I need the denominators to be the same, and they're flat out completely different. So I have to multiply them by each other to make that work. So on the first one, I have to multiply by x squared over x squared. And on the second one, I have to multiply by x squared plus 2xh plus h squared. And of course, to fix the denominators, right, multiplying them means I have to multiply the numerators too. So in cleaning this up now, the denominators do match. They're still all over h. The denominators are x squared and x squared plus 2xh plus h squared, and I really don't want to multiply that out. That's not in my best interest, okay? So we're going to leave that in factored form. And in the numerator, I have x squared minus, and do you notice this negative? It will distribute through all of this. So I have minus x squared minus 2xh and minus h squared. Super crazy lot going on my screen. I need to move it. Okay, I earned a little more space by doing that. What do you notice simplifies in the numerator? Yeah, the x squareds add to 0, so they eliminate one another or cancel out. At this point, I feel like I've got a fraction inside of a fraction. Are you guys feeling that way too? I've got a fraction in the numerator, and then I've got a single denominator. So we can change that so that they are a single fraction by multiplying by the reciprocal here. So this h and the 1 over h. So I could actually change this so that I now have negative 2xh minus h squared over, and then I've got h x squared, and then x squared plus 2xh plus h squared. Okay. I know it still looks really messy, but it's actually in a really good position now. Because do you see how the numerator, all the pieces in the numerator have an h in them? Everybody see that? That's what's going to allow this h here to cancel out, which is in fact the goal. I want it to go away, because until it goes away, I can't plug h as 0 in. I can't substitute the h as 0 in. So in the numerator, I'll go ahead and do it this way this time. I did it the other way the last time. I can eliminate one of the h's from each of the terms. And that leaves me with the limit as h approaches 0 of negative 2x minus h over x squared times x squared plus 2xh plus h squared. And the reason I don't need to worry about like the parts that are in parentheses or what's still in my denominator, like why didn't you cancel an h out of that? Because it was all multiplied. The h had already been factored out of that. So the h in the front really is a factor of everything inside. So it is being eliminated. It just doesn't look quite the same. But you know what? As messy as it is, it's about to look really nice really quick, because now I can let h be 0, right? So I have negative 2x minus 0 over x squared times x squared plus 2x times 0 plus 0 squared. All right, you don't necessarily have to show all of that, but that's what we're doing. We're plugging in 0 everywhere. So this leaves me with negative 2x on top, and these pieces both equal 0, so I have x squared times x squared, or x to the 4th on bottom. Always reducing, right? So negative 2x over x to the 4th will become what?
2x over x to the 3rd, or negative 2 over x.
Right, negative 2 over x to the 3rd. That's what we would have. Very, very good. All right, so one more sort of extension of what we're doing is that what we're finding here, what we found over on this one, was the actual slope. The slope was negative 2. But it's only good at the x value of 1, right? When x is equal to 1, the slope is 2, negative 2. That's specific. The nice thing about this one is that now that I've got a formula for it, I could tell you, okay, or I could ask you, what's the slope value when x is equal to 0? And you would have to say it doesn't exist because that would be 0 in the denominator. That was a bad example. All right, so I said, what is the slope value when x is equal to 3? And you could plug the 3 in and you could just answer for me. And I say, okay, well then what's the slope value when x is equal to 4? And you could plug a 4 in and you could answer for me. So this is a really nice form of a way of doing it because I'm able to answer lots of slope questions from the same work that I did. Over here, if I now ask you, well, what's the slope when x is equal to 2? You got to do the whole process again because I don't have an equation that tells me how to find that in general, right? I only know it for one very specific location. And over here, I know it in general for any x value. So not only can I find the slope, but sometimes I'd like to actually find the equation of the tangent line itself. And that's what we're asked to find on the next example. It says to find the equation of the tangent line, and then we're going to use a graphing utility to graph it. Okay? So the nice thing about asking this question is that you could actually verify visually very quickly, does my graph make sense? Did I really find what I thought I found, or did I make some mistake that I need to go back and fix? Now, again, this is a different kind of function. I did polynomial, that was the first example. We did a rational function, that was our second example. And now we're going to do a square root. Okay? I'd like to do it in general, because my preference is always to do it in general. I think it's actually a lot easier than working with all of the numbers through the problem to use it in general. If you want to put the number in as 1 at the beginning so that you're doing it more like we did this problem, you can do that and it will be okay too. Either way will work. So I'm going to choose the general form, which again looked like this. And we're ignoring this 1, 1 until the end. I'm not going to touch it at all until the very end of the problem. Okay? Ignoring. But I can't ignore the function because the function itself is telling me what I have to do for the different pieces in the limit problem. So the limit as h approaches 0. So on the first part it says f of x plus h. So that's the part that I actually have to replace the x with x plus h in. And that x is located underneath the square root, so now my x plus h will be located underneath the square root. The second part is what I get for free. It is the function I'm given, so it's square root of x. And the denominator is part of the process as well, stays the same every time, it's just h. Okay, we've done this problem before. It didn't have an h in it, it would have had a number in it, but we did it before. In fact, it was on your test, but I asked you to do it in a table form and not an algebra form on your test. When we're trying to get rid of the denominator, what we do is we actually multiply by the conjugate of the numerator. Remember that? So what is the conjugate of x plus h, sorry, the square root of x plus h minus the square root of x? Yeah, it's the same thing, it's just the sign changes between my square roots from negative in this case to positive. So I'm going to have the square root of x plus h plus the square root of x, and I'm going to do that on the top and the bottom. Now the goal, or not the goal, but the purpose in doing that on the top is that it eliminates the radicals. So the first two multiply together, right? X, square root of x plus h times square root of x plus h, and I get x plus h. The last two terms multiply together also well, so I have square root of x times square root of x, that's x, and it's a minus because there's a subtraction sign in front of one of them. And then the inside and the outside terms are identical with opposite signs. Right? So I don't have to worry about the inner and the outer terms on this one. In the denominator, I don't really want it to be distributed out. That's not helpful. If my goal is to cancel out the h, don't distribute the h. Okay? So it's going to be left in that same factored form it already looks like it's in, like so. So what's going to happen in my numerator now? Okay, the x's add together, they cancel out. Did you say something else in addition? Same. Yeah, we combine like terms, exactly. So these x's add together. And then what does that leave in my numerator? An h, right? Yeah. The h that is still remaining in my numerator will be what eliminates the h in the denominator, which was the goal. You can do that in one step if you'd like, instead of 2 steps like I did. But please remember that that does not mean that you do not have a numerator anymore. What's your numerator? 1. Because we've divided, and when you divide, you get 1. H divided by h is 1. And then my denominator, x plus h underneath the square root plus the square root of x. Right? Can h equal 0 now? It can. And yes, I know there's an h in the denominator, but this h in the denominator is not going to make the whole denominator 0, which was the problem with the first one. This h is okay. So on this one, I have 1 over, and I have square root of x plus the square root of x, which looks suspiciously like 1 over square root of, or 2 square roots of x, I mean. You might be bothered by the fact that I have a square root in the denominator. Don't be. This is just a formula for finding the other, what we're actually asked to find. We're asked to find the equation of a tangent line. All right? So what we actually found is slope in general. But we don't have slope in general. We have something that we ignored from the very beginning, right? We ignored the ordered pair 1, 1. So we need to go back and we need to actually use this. So this is my slope equation. My slope, which is f prime of x, is 1 over 2 square root of x. And I want to do this at the x value of 1, because that's the value I was given. So what do I get when I plug 1 in here? I get 1/2. All right, so let's take a look then at how that helps us to answer the question that was actually posed. The question actually posed was to find the equation of the tangent line, not just the slope. Well, can somebody give me a general equation for a line? There's more than one, and we can do it from any line you give me, so what do you want to use? An equation of a line. Awesome. Let's use that one. Okay. We know m. It's what? 1/2. We don't know b, but we do know 1 point on our line, 1, 1. So if I let x and y each equal 1, I can find b. What would b equal? It's 1/2, that's right. Right. So I'm going to subtract it from the side. If that bothered you, I kind of shortcutted some stuff there, but oops. This is 1/2, and if I subtract the 1/2 from each side, 1/2 minus 1 would be 1/2. So my equation, part A, my equation is y equals m, which is 1/2, x, plus b, which is also 1/2. They do not usually match. That is not normal. All right, grab a calculator. If you don't have yours with you, look on a neighbor's real quick. And I would like for you to graph the original function, y equals the square root of x. And then I'd like for you to graph the line we just created. 1/2 x plus 1/2. And feel free to use decimals if you'd like. And just, I think a standard window, probably a zoom 6 is probably sufficient. You may want to look at just from 0 to 10 on both of them. Actually, might be a little bit zoomed in better. So the square root of x looks something like this. And the x value of 1 is like right over here. And if we've created the right equation, at least should be convincing, I'm going to move mine, that it created the tangent line at that point. At the very least, if you see it doing something like that, we got problems, right? You're like, that's not the right one. There's something I did wrong. Okay, so that's what we would do for part B. You would draw a sketch verifying that you've actually taken a look at that. So anytime that it says use a graphing utility, that's great, but I still need to see what your graphing utility did. So draw me a sketch of what you're seeing, okay? All right, so I actually mentioned a couple of these already, but there are places where derivatives don't exist, where slopes don't exist. In particular, there are 3 locations where slopes do not exist. Discontinuities. Tangent lines do not exist at discontinuities. So in particular, the limits can exist, but the tangent lines cannot exist at holes, and neither one will exist at a jump. So no holes, no jumps for tangent lines. Okay, so none of that can happen. The next one is one we have not seen happen yet, but I'd like to argue why it can't. Anything that's a sharp turn. So if it's not smooth, smooth and continuous are not the same thing. This is definitely continuous, but it is not smooth. There is a definite change in direction at that point. It turned. So if you can imagine trying to draw tangent lines on either side of this, you run into problems. So on the right-hand side, it would look a lot like these lines, right? But on the left-hand side, what would your lines look like? Well, kind of like this. So there's no smooth progression of one line turning into the other one. It doesn't work because the curve itself isn't smooth. So any sharp turns do not give you tangent lines. And the last one is a vertical tangent line. So this one rarely happens, but just so that you're familiar with the idea, if you had a very sharp graph that ended up looking like this, where it was super tight and ended up with a vertical tangent line, we would say that that tangent line, the slope doesn't exist there either. So the derivative would not exist because the slope would be undefined. The line exists. There's a line, but the slope itself, it doesn't exist because it's an undefined value. Now, you might be looking at that and saying, well, it seems like there's some sort of a relationship then between whether graphs are continuous and whether or not they actually have derivatives. And there is a relationship, at least it's a one-directional relationship. If you have a derivative, if it's differentiable, then you automatically have something that's continuous. But you can't twist that around and go the other direction. And a prime example is what I drew on 2 and 3. On 2 and 3 over here, they were continuous, but they were not differentiable at some location. But if we have things that are differentiable, then we know that they are going to be continuous. So let's take a look at an example. It's an interesting one, the last one in this lesson. It's an absolute value of a polynomial. So I had someone talking to me, I don't even know if it was in this class or from my other business calc class, that said, but don't absolute values give you V shapes? And I said, they do sometimes. If you have the absolute value of a linear function, you get a V shape. This one's not a linear function, so it doesn't actually give you a V shape. So it's interesting though. So on this one, we have the absolute value of the equation x squared minus 9. So before we discuss it too far, if the absolute values were not there, what would this look like? It's a parabola. So bear with me for a moment while I can show you where this is actually coming from so that if you can't figure out how to make your calculator show you what you want to see, you can at least reason through it in a way that makes sense. So this graph would have looked something, oh my goodness, try that again, like this without the absolute values, right? And the reason I know it's opening up is because the x squared is positive. The reason I know that the y-intercept is negative is because it's negative 9 at the end. Now, absolute values say that whenever I get out of an absolute value needs to be positive. So right now on this graph, down here, would not be existing on an absolute value graph. So what happens is that whatever's below the x-axis gets flipped to being above the x-axis on an absolute value graph. So the image we end up getting looks like this. Roughly speaking. Okay, the red graph here now is the graph of the absolute value, roughly. Okay? It crosses at 9 on the y-axis. It has the same, endpoints pointing upward, just like the parabola did, but it bounces off the x-axis and it has these, what? What's happening now here? It's continuous, right? There's a sharp turn there, right? So the question actually asks you to find or to describe values where the function's differentiable. So before it was an absolute value, it was smooth and continuous, and it was just a great function. It was perfect. And it had derivative values, tangent lines everywhere, no problem. But once I did this reflection up from what was underneath the axis for the absolute values, there became two sharp turns, right? There became problems with my derivatives, in particular at these two locations. So these two locations are causing me problems, but they're the only ones, right? Everywhere else is good to go. Everywhere else doesn't have any of these issues. There's no other sharp turns. There's no other, there's no vertical tangent lines. I don't have any discontinuities. Everything else is good to go. But I do need to figure out where it's having these sharp turns. How could I find where it's having these sharp turns? Okay, you could use a calculator. This one's actually really easy to do by hand. Yeah, it's going to be wherever the wherever the function equals 0 or hits the x-axis. So in particular, it's where x squared minus 9 is equal to 0, because this line is the line where y is equal to 0, right? That's what the x-axis is. Well, x squared minus 9 equals 0 is a pretty straightforward one to solve. If it weren't, your calculator might be a nice choice, but what values do I get out of this function when I solve it? What is it? Plus and minus 3. And at these places, Eric, you told me already, these are sharp turns, right? There are sharp turns at 3 and negative 3, and those are places where I don't have derivatives. So how could you write this answer? Well, there's a couple of ways. You could say, if you're writing it out sort of in English form, is at all x values except 3 and negative 3. That'd be great. It's differentiable at all x values except for 3 and negative 3. WebAssign might ask you to actually write it in interval notation, though. So interval notation means starting at the left-hand side of the graph. Left-hand side would be negative infinity. And it will have derivatives. It will be differentiable until I get to what value? Negative 3. Yeah, at negative 3. And I'm using parentheses because, number one, you can't equal negative infinity. That's a concept, not an actual numerical value, right? And I can't equal negative 3. That's the whole point, is that I have a discontinuity at negative 3. But right after negative 3, I have more values. From negative 3 to what? To positive 3. And then I have more values from 3 to infinity. So that would be another way of doing that. Yes, sir. Your WebAssign might. It's 6 one way, half a dozen the other on resources that do. So if you want to put them in there, they'd look like that. And WebAssign may require it. I'm not sure. It's possible. Yep. If you're writing this out like on a written homework or on a quiz at some point and you write it like this, I'm okay with that. I don't have a problem with that at all. Okay. Obviously, you can see why WebAssign might not like that, though. It's harder to do right, wrong kind of grading if you've written it in that form instead of the interval notation form. So, any questions?